the transmission of an electromagnetic wave which is incident on a new medium or in a specific boundary. And this boundary, so let's write it somewhere here. So we have an incident wave. Let's consider this one the Ki, the incident wave, and the wave it is going to be reflected backwards, the reflected wave, and we have also the transmitted wave. So part of the energy of the wave, it can be transmitted. Now, the first example that we covered, it was the incidence on a perfect conductor. So if we had a perfect conductor, we noticed that we have no transmitted wave, and because of the boundary conditions, which have to be satisfied right here at the interface, okay? So we have an interface, and this interface is not absorbing any energy. So no energy is lost or no energy is created right there. So the energy conservation issues can be considered at these specific boundaries. Wait a second. And regarding this, we can see an example. So let's assume that we have a wave propagating in this is x equal to 0. This is propagating along the x positive. This would be the incident wave, and more parameters. We have the E incident. So we have a wave which has EI and HI, the incident electric field vector, and the incident magnetic field intensity vector. So for this wave, it is polarized. Polarization is AY. Okay, so let's say this is how it is polarized. Then we have also the K, the propagation vector. This is equal to K times AX. Okay, so this means that the wave is. We assume that we have a frequency which is 100 megahertz. Given that 6 millivolt per meter, so we this incident is done on a perfect conductor. So if this is the perfect conductor, the question is, let's find the EI and HI. So let this be the first question, and we know that. So let's write first the electric field, the vector, which is associated with the incident wave. So here we have the EI as a function of Z, without including the time dependence for a moment. This one would be equal to, so first of all, we have to write down what is the direction of the electric field. So direction of the electric field, we can notice it because we are given that the wave axis polarized. We can denote this as the direction of the wave like this. So this is AY. Then we multiply this one with the, wait a second, so we have E0, E incident 0, this is the amplitude, times the E to the power minus J beta 1 x. Okay, so this is the wave, the electric wave associated with the propagating plane wave, and then we have to write down also the HI, so the incident magnetic field intensity vector associated. First, we need to determine what is the direction of HI. So we have the wave is traveling along the axis, the electric field is pointing along the y-axis, and the magnetic field it is pointing from the board. You because this is x, this would be the y, okay, and the z is a cross product of x with y, so we get this direction. So here we have that for the H, for the magnetic field intensity vector, we have here Az times the incident electric field E0 divided by the intrinsic impedance. So the ratio between the electric field and the magnetic field, it is always equal to the impedance, intrinsic impedance, and this would be minus J beta 1x. So this space propagator, this is not going to change. Okay? We can substitute in these values a few parameters, where the first one would be the 6 millivolt per meter. So we can denote this one as, we can write this one as AY times 6 times 10 to the power minus 3. This is the millivolt per meter, times e to the power minus j. Now we need a beta. How can we find the beta here? And the beta is equal to omega divided by the c, or we often see this one this way, mu epsilon. Okay. So since we are given no specific parameters, these values we consider the vacuum values, or let's assume variability. Here we have what is omega, the frequency. So frequency, this is going to be 2 pi f. Okay, the frequency is this one. So here we have 2 pi times 10 to the power 2, which is 100, times 10 to the power 6, which is a megahertz. This is the omega, this one, and the square root of permeability times permittivity, the speed of light, 3 times 10 to the power 8. So in this case, we just cancel out these, and we are left with 2 pi over 3. So this is the beta. Here we have 2 pi over 3x. So then, since this is vacuum, then the amplitude for the magnetic field component is going to be equal to 120 pi. So this makes this equal to 6 times 10 to the power minus 3 divided by 120 pi. We need also the direction, which is AZ. So here we insert AZ right here. Times e to the power minus j, e to the power minus j, 2 pi over 3x. Okay, so these are the waves which represent the incident wave. For the instantaneous expression, what we need to do here is that the instantaneous expression, we just multiply, so we do here E incident as a function of, wait a second, this is not correct actually. Do you notice anything wrong here?
Professor, aty ku janë klapat e Z-it do të vesh X.
Yes, that's true. So here, since we are propagating along the x, that means that only if we plot the wave as a function of x, this is where it's going to change. Okay, so we put here x, then we get here also electric field as a function of x and time. This would be equal to the real part of the phasor, and the phasor, it is AY times 6 times 10 to the power minus 3. What is the rest? E to the power j omega t, because we have to multiply with the time propagator, and then if you like, we can factor out e to the power j, and this is minus 2 pi over 3x. Okay, and in this expression, it is clear that this is a constant, this is a constant, so we can take them out of the real part, component, so we can take this out immediately. And we have this is equal to AY, the propagation is the same, 6 times 10 to the power minus 3. And then we have the real part of the exponential term. So the real part of this e to the power j omega t, this is simply the cosine of omega t, and actually omega, we can find the correct value of omega, which is, what is omega? Omega is equal to 2 pi times 10 to the power 8 radian per second. Okay, the unit is radian per second, so let's write this one, radian per second. So here, we get here 2 pi times 10 to the power 8 time omega minus 2 pi over 3x. So this is the electric field, and the next, yes, the magnetic field intensity. It is going to be pretty much similar to these, especially including this term, and the amplitude will be modified, including also together with the amplitude. Let's figure out actually what we should also modify the direction. So we have to determine correctly what is the direction of the magnetic field intensity. That one is going to be H incident as a function of x and time. This will be equal to AZ. This is pointing along the z direction. The amplitude is equal to 10 to the power minus 4 over 2 pi just give me a second. So you can notice that 6 times 10 to the power minus 3 divided by 120 pi. This is what we converge to. And then okay, so these are the, yes.
The direction of the magnetic wave is AZ, not AY.
That's true. Okay, this was AZ. Okay, this is AZ because this is AX, AY, and the cross product between these two is going to be the direction of the. No, wait a second. Actually, the more standard is this one. The direction of the electric field. Let's try this one. The electric field across the magnetic field intensity. This would give the K. Just for the direction. I mean, the amplitude is going to be, it's not going to be the same, of course. But we, in fact, the product between these two, so this is only the direction, but including the magnitude, we are talking about the pointing vector. Okay. So the pointing vector S is equal to the cross product between these two vectors. Now, these are the incident waves. Now, regarding the reflected wave is what? So, first of all, since this is a conductor, this means that no wave is going to be transmitted. We just have reflection backwards. And at this moment, we can also state that we're going to have a standing wave. Okay? So we're going to have a standing wave. This is what happens. Then the electric field intensity at the conductor here is going to be equal to 0. And the magnetic field intensity at the surface, it's going to be maximum. So H is going to be, let's draw the H in black. So we get this. Okay, so H is in black, this is H, and here we have the electric field, which is in red. Why is it 0 at the boundary? Because you know the electric field boundary conditions, they report that the electric field in medium 1, so this is medium 1, and this is medium 2, they have to be equal to each other. So the boundary condition, the BC, this states that E1, it should be equal to E2. And E1 and E2, we're talking about different mediums. So since on E2 is equal to 0, immediately we also get that at x is equal to 0, this is also 0. So let me write this x equal to 0. Okay, because of this boundary condition, we apply a lot of these kind of relationships. Now, for the reflected wave, what the reflected wave is going to be, here we can put here E reflected wave as a function of x. This is going to be the same expression, only that it is going to have a negative sign in the... So what difference, can you help me here? What difference do we need to make in this expression, which is for the incident wave? How is it going to change? So this one that we circled, so let's give this one, this is the incident one. How can we change this to draw the reflected one?
Te kosinus supresor do ndryshosh vetëm atë minusin.
Yes.
Dhe bësh plus në fund.
This becomes a plus, right, for the reflected wave. So let's do it like this. So, so that becomes a plus for the reflected wave. Anything else?
Te kjo jo, po tek fusha magnetike,
Yes.
there will be two minuses.
So here we need to put a plus here also, because the magnetic field also is going to travel in the negative x direction. But
there will be a phase difference.
The phase difference between which ones?
There will be a phase difference.
Between which and which?
The magnetic and electric fields by pi over 2.
Okay. But what about the amplitudes of the electric fields here? So we're going to write here the reflected wave. We need also a negative sign here. Okay. So it's best if we write this one completely. So the reflected wave, this is as a function of x and time. This is going to be equal to minus ay times 6 times 10 to the power minus 3 times cosine of 2 pi times 10 to the power 8 time plus 2 pi over 3 x. So we need this negative sign here because actually, let's take this away. You correctly corrected them, but let's give this. Let this be the incident wave. And when we insert x is equal to 0, where x is equal to 0 is right this interface, we see that wait a second.
Professor, in the electric field,
yes,
I think you may not put this minus sign before the y direction.
Okay, why?
Because both incident electric field and reflected electric field go to the y direction. If you change the sign, you may do it for the magnetic field, I guess.
But let's think about this one. So the boundary condition, we have here that the right at x equal to 0. So this is the interface. The interface, we have located it right here, okay? And we should have the following. E1 should be equal to E2. But what is E1? E1, it is composed of incident wave plus the reflected wave. So here we can write it like this. E incident plus E reflected, okay? This should be equal to 0. Okay, this is the this is what the boundary condition states. And what we can also do is that if we insert x equal to 0 here, and let's set time equal to, so they actually, this term will be the same. So what can you say about these? When will the E reflected plus E incident be equal to each other? So let's write here equal to, Let's set x is equal to 0. We get 6 times 10 to the power minus 3 times cosine 2 pi times 10 to the power, I'll give you some more side. Can you read this part here? And this is equal to, we don't know, let's say this is 6 times 10 to the power minus 3 cosine 2 pi 10 to the power 8 times t. So if we add these two together,
A już buty do Uber Story, już internet jem.
Shkolla mua. Se ke vetëm për ti problemin.
Ik gjë gjë për vete.
Okay. Okay, can you hear me?
Professor.
Okay, sorry. I was just out for a moment, but it was frozen. Po vazhdoj po flisja fakt, po thashun kur ju nuk po flisin shumë, I just went back. But thanks for the patience. Okay. Thanks, Andy. Okay, let's continue. Let's continue where we left. This was a small break, but so are we convinced now that the amplitude of the reflected wave should be negative? So we were discussing this part here. So this means that in this case, in order to satisfy the boundary condition, the reflection coefficient should be -1. Okay, the reflection coefficient and the transmission coefficient, they are defined as, so let me write them somewhere here. So the reflection is going to be equal to R, the ratio of the reflected electric field to the incident electric field. So this is going to be equal to -1. And the transmission coefficient, this is going to be equal to the transmitted electric field divided by the incident electric field, which is 0. Okay. So the reflection coefficient, it has to be equal to -1. Sorry, it looks like you don't see everything. Yeah. Is it clear now, Christina?
Yes, thank you.
Okay. There was another comment by Besmir, and I want Besmir to listen carefully. Besmir, you mentioned that the magnetic field should be out of phase with the electric field. Is it what you said?
Yes, by pi/2.
Okay, but
The reflected ones.
Which one? Do you mean you want to make out of phase the reflected H?
Yes, the reflected one.
Okay, but why? Where do you see this? Where do you see?
Practically, I see it on the graph you have drawn over there.
Yeah, that is a good point. But let's see. In fact, let's think about this problem this way. In the same wave, the electric field and the magnetic field, they are in phase. Okay, because we are in air. We are not in a conductive medium. But what we see here, we can remind ourselves this here that these here, they are not the waves. Sorry, they are not the incident and the reflected waves. This is the wave in medium 1. And the wave in medium 1 is equal to the incident wave plus the reflected wave. So the summation between these two have to be out of phase, okay? But not the incident and the reflected one. Is it clear? And let's have a look at the reflected wave. So the reflected wave, so we did the electric field. What about for the magnetic field component? That one will have, well, actually is the best. So the incident wave, it looks like this. The reflected wave is going to look like, this is the K reflected, okay, KR. The electric field, this is the ER. So what should be the direction of the magnetic field in order to get this? So this is pointing down, and wait a second, so this KR, this is minus AX, okay? This should be equal to the direction of ER. ER, this is minus AY, cross product with what? What should we get here? So here we have AX, AY, and AZ. So we get negative AX, this is minus AY, cross product, this is going to be AZ, but what type of AZ? This is minus AY cross AZ, this is AX, okay, that's true, this is plus AZ. So from this cross product here, we can use this to determine the direction of the magnetic field. This is going to be AZ. This is not going to change. So which means that the incoming magnetic field vector intensity is going to look out of the board. It's going to look this way. And when it is reflected back, the H is still not going to change. It's going to point out the point. Incident the same, the reflected the same. The only field or the only vectors that change direction, it is the electric field, which becomes negative because the boundary condition has to be satisfied, and the direction of the KR. Okay, so we have, maybe it's best if we draw them again. So this is K incident. The electric field, I think we draw it like this, and the magnetic field is going to come like this out of the board. And when these are reflected, this is KR, the electric field is going to point down, and the magnetic field is going to point up. Okay, so these are this will be the triplets of the weight or the vectors. Okay, so with these now we can try to determine what is the E1 and E2. And we can erase this part, find. So E1, the electric field in the medium, in the first medium, should be equal to incident plus electric field reflected. Okay. Now the similar expression we have to do it also for the other wave, but now what we need to add here, we need to add this phasor, okay, with another phasor which is going to be like this. So E reflected, this is equal to minus AY, right? EI0, e to the power plus j beta 1x. Okay, so when we add these two components, what do we get? If we add these two phasors, we have the expressions that should look like this. E to the power minus I theta minus e to the power plus I theta. So now you write this somewhere in your notebook, and you're going to observe that the cosine terms will cancel out. The only term that will survive, it will be the sine term, okay? Because this is equal to, I think it's obvious that we get a sine term from this one, right?
Yeah, that's all.
Yes, so in here we should get the sine term. So if we add these two together, we get the following. We get minus AY, this is the negative sign, times J times 12 10 to the power minus 3 sine 2 pi x over 3. So this is the beta x. Beta is 2 pi over 3. So this is the electric field in the...
Professor,
Yes.
кто проблем в этом minus y at the reflected electric intensity. I can we distinguish between the opposite direction and the right direction, but e times e to the power minus j beta 1z, the e to the power plus j beta 1z.
Yes.
The Nictona Tragonchi on a different, same axis, but in opposite directions.
Yes.
For 7 doesn't have minus AY at the guard.
Okay, let's try to convince ourselves like this. So, wait a second, so let's take this away. So normally, we have the incident wave, we write it like this. We say that E incident, this is equal to, so what is a given? This is AY, okay? And this is, so we are going to represent all the other components as a function of this. Kjo është e dhënë, dakor? Pra, këtë s'po e ndryshoj. Çdo gjë tjetër ndryshon. Pra, incident wave is AY, EI0, e to the power minus j beta 1x. That's correct, right? What is the reflected wave? The reflected wave, this is equal to AY, okay, times E reflected 0, which is the amplitude, e to the power plus j beta 1x. Do we agree here? As we said, this is a given. We have to figure out what is ER0. Now, we know the following. We know that if we add these two terms together, which will be the following: E incident at x equal to 0, okay, plus E reflected at x equal to 0, this should be equal to what? This is the electric field in medium 1. Is the total electric field that we have on one side of the interface, okay? And this is also when at x equal to 0, and this is equal to the electric field in medium 2 at x equal to 0. Are we good so far? Are we okay here?
All over.
Okay, so what is the electric field? Your question is a very good one. But, okay, let me try to separate this here. So, what is the electric field in the second medium?
0.
Yes. So, this also has to be equal to 0, okay? So, because of the boundary condition, it has to be satisfied, which means that here, we said that what is the electric field when x is equal to 0? What is exponential to the power 0 is equal to what? It's 1, right?
Yes.
So this is a 1. So at the boundary condition, this is 1 and this is also 1. So we multiply them by 1. Then we get the following. We get that AY times incident wave 0 plus E reflected wave 0. This is equal to 0, right? Now, this is a given, independent variable. This one is dependent variable. So in order to add the 0, what is the amplitude of the reflected wave? We say ER0 should be equal to minus E incident wave 0. Okay? So this is it clear now?
Yes, yes, it's clear.
Okay,
Thank
so
you.
this looks like, you're welcome. So this looks, we can say again what we wrote before a moment. We said that the reflection coefficient, it is always defined as the ratio between the reflected wave component over the incident wave. And in the case of a perfect conductor, this is equal to -1. Okay? So, and this is what we observe, so it changes the direction. So that's why we get this term. And then I hope this is also clear because e to the power minus I theta, this is cosine minus theta, minus sine minus theta, minus cosine minus theta. So here you can see that the cosines are cancelled out. And finally, we're going to get this wave. Sorry, we have also the j here. I forgot. And we have also minus theta plus, or what is this? A minus j sine minus theta. Okay, so yeah, this is where we get this. Finally, this is the electric field in the first medium. For the second medium, all we do is that we have to add. This is AZ. This direction is not changing. 10 to the power -4 over 2 pi times cosine 2 pi times 10 to the power 8t plus 2 pi over 3x. This is the reflected. So let's write here, this is the reflected wave. And the incident wave, sorry, let's give this is like this. So we need to add these two terms. So in principle, we are going to add, this is going to be something like this. So when we add the phasors of the incident H and the reflected H, if you allow me, we can, which part can we erase? I believe we can erase this part here. We don't have, wait a second, no. Okay, maybe we can see it from here. So this is the incident gauge. And let's take this out just for a second. The reflected H is going to be the following. We have H reflected as a function of x. This would be equal to AZ times the amplitude of the wave is going to be the same. So incident over eta 1 e to the power plus j beta 1 x. So if we add these two terms together, we know that when e to the power j beta is added with the e to the power minus j beta, we have e to the power I theta. This is cosine theta plus j sine theta. E to the power minus I theta. This is equal to cosine theta minus j sine theta. So when we add up together these two terms, it is clear to all of us that the summation here is going to produce 2 cosine theta. So we're going to have, so here we observe that for the magnetic field and the electric field in medium 1, we're going to observe this phase difference, okay? Because one is sine, the other is cosine, which means that sine at x equal to 0 is this electric field in red, but for the h, it's going to be another expression, which we can write it right away. So the incident electric field and the magnetic field, we have not erased them yet. So you can see them how they look like. And now we need to write the H1, which means that this is H incident plus H reflected. And this would be equal to AZ, this is plus, times 10 to the power minus 4 divided by 2 pi times 2 cosine 2 pi x over 3. You can cancel a couple of 2's, the amplitudes they look as they are, but here we have the magnetic field intensity in region 1, and we know that cosine at x is equal to 0, it's 1, so it's a maximum value. This is where we have it. For the electric field, is the line in red, as we mentioned. So this is the electric field. You don't need to redo this again. Okay, and then now that we have these phasors, we can also construct the. So let's not forget, we have no time here, right? Because we have added just the phasors. Okay, let me write this one. This is phasor, phasor. In order to add the time, all we need to do is that we just multiply these with phasor times e to the power j omega t, e to the power j omega t, and we calculate the instantaneous expressions. So this property of sine and cosine, this was clear. So the only thing that we can observe here is that the electric field, it has a negative j here, okay? So so we can say here E1 as a function of x and time, this would be equal to, if you allow me, we can take this out of the real part right away, okay? Because we always know that E as a function of x and time, this is going to be equal to the real part of E as a function of x, okay, times e to the power j omega t. So this is what we need to do, but from the real part, we can take out these terms which are constant. And with this, I mean, we can take out this 12, 10 to the power minus 3 sine. This is not going to change, this is the real component. So if we take that out, and from this expression, we can take out these, okay? And taking them out, I mean the following. This is going to be equal to minus Actually, let's keep the minus inside. If we keep the minus inside, we can write here for the electric field, we can say this is AY, okay, times 12, times 10 to the power minus 3, 10 to the power minus 3, times sine 2 pi x, times sine 2 pi x over 3, times, we have minus j. Now, here, we do the real part, okay, of minus j times e to the power j omega t. So here we have minus j e to the power j omega t. Now, what is minus j?
Știm cu 5 minus j, 5 un pic de dat.
So this is 1, Christina, right? This is minus 1. This is I or j. Let's write this j. What is j? E to the power j times pi over 2, right? What about minus j? Minus j is e to the power minus j pi over 2. So we just rotate by minus pi over 2, we get minus j. Then we go this way plus j. So here we have e to the power minus j times pi over 2, that's minus j, times e to the power j omega t. Which means that here we can factor this out. This would become, we can also write like this, exponential of what? J times omega t minus pi over 2. So what is the real part of this term? It's going to be equal to the cosine omega t minus pi over 2, right? So we have here cosine omega t minus pi over 2. So this whole term, this will be equal to, so we have all of these constant numbers. We can write here ay times a lot of these numbers. And let me write here a real part. So this is equal to cosine omega t minus pi over 2. Now this cosine omega t minus pi over 2, this is equivalent to what? Who can memorize this one?
Sine omega t.
So let me write here, this is a constant, okay? With constant I mean all of these constant terms. And this is, you said, are you sure it's sine? I always, I'm confused with these. This is cosine omega t minus pi over 2.
I think it's minus sign.
So if we think different things, let's try to draw them and let's try to derive them. Let's make a narrow angle. Narrow angle, I mean, let's do an angle like this, okay? And we are looking for cosine omega t minus pi over 2. So we are talking about not this angle here, but we're talking about this angle, right? And the cosine of this angle here, so we are just taking minus pi over 2 down. What is the cosine of this vector here? Is the projection on the x-axis, right? So is this one. Would you agree? So this cosine is in fact this length, which is positive. And again, this is omega t, is this angle here. And the cosine of this angle minus pi over 2 is this length. Now, this length here, it is equivalent to the sine of omega t. So Christina was right, but I just wanted to double check because it might get confusing if it is one way versus the other. So here we can have ay times constant terms. With constant terms, I mean everything from here to sine. Okay. Times, actually it's best if we write all of them because it's time to write the final result, but I think we confirmed what Christina correctly told us that we need to write. So here we have 12, 10 to the power minus 3 sine 2 pi x over 3. Now we are left here. Then we have sine omega t, right? This is sine omega t. Okay, this is the complete expression of the electric field in medium 1. Now, we did all of these steps. We can erase these. I hope this is clear. We can always redo these. Just that we need to figure out the value of 1 minus j term, which is extra. When we look at this expression of the h1, we can say here h1 as a function of x and time. This is equal to az times 10 to the power minus 4 over pi, 10 to the power minus 4 over pi times cosine times, what do we have here? The cosine of, so what do we get from here? So if we multiply with e to the power j omega t, what is the real part of e to the power j omega t?
Cosine omega t.
That's true. So we can simply say here, cosine omega t. So we can keep this simpler, or the only difference would be that, so if you allow me, we can stop it here, but it looks like the electric field, it is sine sine, the magnetic field, it is cosine cosine. And so they are, yes, they are out of phase as a total component, yeah. And this is more clearly observed when we see here, when we see this as a function, wait a second. And in fact, we can also observe that they are out of phase in time, because the previous expression, this is cosine omega t, and this is, sorry, this is cosine omega t minus pi over 2, and this is cosine omega t. So at the same instant in time, this is leading. This h is leading because this has a maximum, and this is still 0. So this is a phase difference. So we can observe here, out of phase by an angle of by pi over 2. This is how we can report these. Okay, is this clear? So here we had an example of how the wave reflection from a conductor, from a perfect conductor. Now, I hope we clarified, and this is also, this can serve also like a good exercise how to work with phasors and the instantaneous expressions of the electromagnetic fields. Now, this was an exercise, and I'm going to erase this one. Do you remember from last time when we did the case, or the general case, where we had lossless dielectric? So if we have a lossless dielectric in this other side, or in medium 2, we have here Ki, this is K transmitted, this is incident EI, and we will get, for the magnetic field, we will have this would be the E transmitted, and the wave, which is coming backward, this is the reflected wave, this is the reflected wave for the electric field, and so we draw this like this, okay, and then we try to determine what are the magnetic field corresponding directions. So here we observe that the magnetic field is going to be this, and in this case we have the magnetic field vector is going to point down. Okay. Now we could draw these electric fields also different. So we can draw the ER pointing it down. So we could, instead of this ER, we could also draw it like this, so we can call this ER. And then we write down the boundary conditions depending on this. But we don't care, we just know one thing, that we're going to consider as a reference, because this is like an equation. What is the independent variable? The independent variable is the direction of Ki and EI. These are the only two, which put a constraint also on the direction of the magnetic field intensity, which is going to point out of the board in this direction. All the rest, all we know for the rest is this Kr and this Kt, the transmitted wave direction. And then, so we can consider also like independent variables. So probably it's good to think in terms of this. So we know the direction of Ki, we know the direction of Kr is reflected, it should come backwards, right? We know the direction of Kt, we know the direction of EI, that's it. We don't know anything else. Then, from here, what can we conclude? What we can find? Well, we can find the direction of Hi. So once we know the direction of all the polarization of the wave, of the incident wave, we can get Hi. Once we get Hi, we can also determine what is the reflected ER, what is the transmitted E, what is the transmitted reflected HR, transmitted HT. And I think this is all, okay? So once we find this, this means that we can determine a reflection coefficient, which is going to be equal to the ER over EI, and the transmission coefficient, which is going to be equal to ET over EI again. So the ratio of the change between the incident wave and the transmitted wave, so the amplitude of the electric field, or transmitted electric field, which are simply represented here, they give to us the reflection coefficient and the transmission coefficient. So this is the reflection, and this is the transmission. And now it looks like how many we have to notice, we have to figure out how many knowns and unknowns do we have in this case, because we had quite a few unknowns, and last time, I think we derived all of these expressions, so we wrote the phasor notations for all of these, and after applying the boundary conditions, we found the following expression. So we found that the ER0, the reflection coefficient, this was equal to the reflection coefficient times EI, 0, and this was equal to the intrinsic impedance 2 minus the first one over eta 2 plus eta 1 EI 0. This was the reflection coefficient. And the transmission, the transmitted wave electric field intensity vector is going to be equal to tau times EI 0. And this was equal to 2 eta 2 over the summation of the intrinsic impedances of two different mediums, okay? EI0. So here we have the reflection and the transmission wave components. And okay. So, given these, we can easily determine. Okay. So let me erase this part for a moment. So, based on the example that we covered before a while, we know the following. We know that the electric field in medium 1. This should be equal to the E incident plus E reflected, okay? And the wave in medium 2, the electric wave vector, the complete one, this is just E equal to E transmitted, okay? Not the complete, the whole. And After we know these, we can, so by adding these two terms here, a second. We get the E1, this is equal to AX EI0 times e to the power minus j beta 1z 1 plus the reflection coefficient e to the power 2j beta 1z. Okay. So this is the electric field, the total electric field vector in the medium one, which is this component plus this component. Okay. Then we have similarly for H1, we have the following: we have AY times incident wave amplitude modified by the intrinsic impedance times the same term, which is minus j beta 1z. And the rest is 1 minus the reflection coefficient to the power 2j beta 1z. Okay, so this is also the net magnetic field vector, which would be the addition of this vector pointing out this way, and this other vector, which most probably is going to point out this way. Because the negative sign between which can appear in here in the reflection coefficient, it can be observed here in this expression. So this can be a positive value or a negative value, which might then cause the inversion of the reflection, what's the name? The inversion of the reflected wave with respect to the incident one. So if the second medium has a smaller intrinsic impedance, then we should get a negative number here. Okay? When it was a conductor, we get -1, because apparently, yes, because in the case of a conductor, this eta 2 would be equal to 0, then we get the -1. So now, given this expression, which actually this expression is full of complex numbers, okay? So if this is full of complex numbers, we know that we can determine from these two terms, we can find that the average power density, time average power density, we write it like this. So this would be equal to 1/2 times the real part of the cross product of the electric field with the magnetic field, but it's a complex conjugate. Okay. So this is what we need to do now. And then to find the complex conjugate of H, we just, so complex conjugate, we know the following. So if we have e to the power I theta, the complex conjugate of this term is equal to e to the power minus I theta. So all we need to do is the following. So we see here that the time average power density, this would be equal to 1/2. Then we do the cross product. So we have the cross product between the E and the H. So we have here AX cross AY, we get here AZ. Okay? And by the way, if we've written here AX, this means that X is in this direction, so this is X. Y is pointing in this direction, and the direction of the propagation of the waves is in the positive Z in this way. So now we just start multiplying all of these terms, and if we multiply here the amplitude of E and H, we get the following. We get here EI0 squared divided by eta, by this intrinsic impedance, because you know that this term here, this amplitude, is going to multiply with this amplitude. We get this. The cross product we get it here. This 1/2 is coming from this term, and the rest is going to be equal to. So this becomes a little tricky. Just let me just look for a moment. So we have E. This is E1 plus J. This is 1 minus. This becomes negative. Yeah. So, what is the first term here? The first term is e to the power minus j beta 1 z. And then we are going to multiply with the complex conjugate of this h, right? So what do we get here? We get e to the power plus j beta 1 z. So it is obvious that if we multiply these two, we get 1. So this will be gone. And then we have the multiplication between 1 plus the reflection coefficient e to the power plus 2j beta 1z times 1 minus the reflection coefficient e to the power minus 2j beta 1z. Why? Because we have to consider the complex conjugate of every term that we can find in the expression of the magnetic field intensity. Okay? So with these steps, it looks like this is going to be equal to 1. So this is pretty much obvious. And then what other terms do we observe here? We see that here 1 times 1, this is equal to 1. Then here we're going to get 1 times this one. This is going to be 1 minus the reflection coefficient. Wait a second, this is minus 1. E to the power minus theta, let's write it like this, plus the reflection coefficient e to the power theta. Okay, I multiplied out this with this. Minus reflection coefficient squared. So we should get, would you agree with this? So you have 2 terms here, there's another 2 terms here. We should get 4 terms. 1 times 1 is 1. Then we multiply this one with the second term. This is minus reflection coefficient e to the power minus theta. Then this is plus reflection coefficient e to the power plus theta minus this square. So if we try to identify to see what we get from here, this is we get this one e to the power theta minus e to the power minus theta. So what do we get from here? And this theta actually has also the j, sorry, right? So we have the j is always there. So what do we get from here? Any idea? So cosine minus cosine, so we cancel. So we should get here 2 sine theta. So combining this term and this term, we should get 2 sine theta modified, and then the average power density is going to be a little simpler, and the final version, wait a second, so this is 2 sine theta, but we have also a j, sorry, I forgot about this one. So these terms here, we should get here a j, but we have forgotten to write a very important parameter here, which is the real part. So this real part, this should stand somewhere here. Okay. Now, with this real part, this means the following. What is the real part of this term here?
E to the power j pi over 2 times r 2 sine theta.
Wait a second, thank you for your interrupt. Sorry for your comment. But let me add here. This is minus the reflection coefficient squared. Now, the multiplication of these 4 terms you can calculate them. But can you repeat it again? What did you say?
I said it's 1 plus 2 times domethënë ajo j është real of e to the power j pi over 2, domethënë është vetëm pi over 2.
Yes, but let me say also the following. What is the real part of j? What is the real part of 3 plus 4i?
0.
No, this
So
is
it's only 3, but the real part of j is 0.
That's true. So the real part of this one is all zero, okay? Which means that this whole term here, this is a real part of 1 plus whatever we have this is simply going to be 1 minus, so this is minus the reflection coefficient squared, okay? So from this whole expression, the average power density is going to be equal to the AZ. This is the direction of the power energy flow, because the energy is going to flow in the direction of the propagation. So this is AZ times the amplitude of an incident wave squared over 2 times the intrinsic impedance times 1 minus the reflection coefficient squared. 1 minus. So this is the average time average power density. Okay. Now, this is the average, the time average power density energy flow in which region? Region 1 or region 2? This is region 1, okay? If this was a standing wave, if this was a conductor, what would be the net energy flow in region 1? It would be equal to 0, because we would have a standing wave. And that would mean that the amount of energy which is incident on this interface, which is separating air from a conductor, from a piece of metal, the same way it will be reflected backwards. So the time average power density, it would be 0 in that case. But now we don't have the complete wave reflection backwards. We have some energy which is flowing to the other side. Okay. So if this is the case, we can also ask the following question, which would be, what is time average power density in region 2? Because this is only for region 1, because we have used E1 and H1. And E1 and H1, this is what they are. Okay, we add up the incident and the reflected coefficients. So this is a good question, and this again would be equal to 1 over 2 times the real part of the transmitted electric field vector cross product with the complex conjugate term of the magnetic field intensity. So it's going to be a term that is going to look like this. Okay. Now, this is something which we covered from the last time. Let's remove this. We also know this, okay? So here we have H1 and so now in medium 2, what is going to be so it should be easy for us because we just need to write the phasors, okay? And what should so in medium 2 we have ET, this should be equal to AX times the transmission coefficient tau times EI0 e to the power minus j beta 2 z. And HT, this is going to be equal to, what is the direction of this one? This is AY, right? So this is going to be AY times tau EI0. So this is the transmitted, the amplitude of the transmitted electric field vector, electric field intensity vector divided by eta 2, because we are needing 2 now. But the intrinsic impedance, the permeability, and the permittivity are different. Actually, often we don't change the permeability too much. When I say too much, maybe you understand. What happens if we change the permeability? What would you expect? Which means the following: the permeability is always equal to relative permeability times mu0. So if mu I is different from 1, what do you observe? So we get a magnetic medium. So often we don't always get a magnetic medium, which means that most of the time, I mean, traditionally, it depends on the problem, of course, we just change the permittivity. If we change the permittivity, we change the index of refraction and other important parameters. And essentially, we also do change this intrinsic impedance. And we move ahead, we say this is e to the power minus j beta to z. So what is the time average power density? This is going to be the following. This is 1 over 2. So let's follow this expression here. What is the direction? What is the cross product of AX with AY? We get here AZ, and then let's multiply the amplitudes. The amplitudes, they are tau times incident wave like this, times the amplitude of the other wave, which is tau EI0 divided by eta 2. So amplitude of the electric field times the amplitude of the magnetic field times the real part of e to the power minus j beta 2z times, what is the complex conjugate of this term? It's e to the power plus j beta 2z. So this is equal to 1. The real part of 1 is equal to, is just 1, okay? So the time average power density in medium 2 for an interface which is from one medium to a lossless dielectric, which is not conductive, we get the following. So this power average is going to be equal to AZ times tau squared EI0 squared over 2 eta 2. This is it, okay? So this is how much power is flowing in medium 2. Okay. Now let's see a couple of examples. So actually, we expect all of us to write down these two formulas on a piece of paper or in a formula sheet, because we're going to use them. Now, this is just okay. So we can take this out. So we have not erased anything essential, so we still have the basic material that we were discussing. Let's see an example here. Let's consider that we have an interface, air dielectric interface. Okay, and in this interface, we have that this air, we know what air is. Air, it has ER equal to mu r is equal to 1, okay? This is air. And then for the dielectric, we have ER, this is equal to 81, and the mu r, since it is a dielectric, mu r, this is equal to 1, which means that this is non-magnetic, air, it is non-magnetic, we know it, and this new material is also non-magnetic, but the permittivity is different. So if the permittivity is different, we see that at this interface, we're going to have some non-zero transmission coefficient. We mean this tau. So the moment we see these data which are given, we can conclude, we can say it implies that this tau is different from 0. Okay? If it was a conductor, this would be 0. No. Now let's see what is the reflection coefficient. This tau, this is equal to in fact, we can derive, I believe, before a few moments, we wrote the following. We said this is eta 2 minus eta 1 over eta 2 plus eta 1, right? So this is how we wrote this one. And this eta, the intrinsic impedance, this is equal to mu over epsilon. So this is equal to the square root of mu, the permeability over the permittivity. So, and we can also write this one like this. This is equal to mu r times mu 0 over epsilon r times epsilon 0. Would you agree with this? Then, so this is the general expression. We can write the following. For eta 2, this is going to be equal to, so mu i's, they are all the same. So we can have here, let me write this as mu r, okay, mu 0 over, let me write this, wait a second. Let me write here 81, okay, times epsilon 0. Minus, since this is air, we can simply write the following. Well, mu r, mu 0 over epsilon 0 over mu r, mu 0 over 81 times epsilon 0 plus mu r, mu 0 over epsilon 0. So how can we simplify this expression? We can completely cancel out. So what we can do is that we can multiply both equations by 1 over the square root of mu r mu 0, which means that we can cancel this out immediately. And we can also, so let's assume for a moment, let's multiply by 1. Multiplying by 1, let's define it like this. We multiply by the square root of epsilon 0 over mu r mu 0. And here we multiply again epsilon 0. So epsilon 0 mu r mu 0. So this term divided by this is equal to 1, which means that we're going to cancel these with these, and similarly we cancel out these terms with this, and the reflection coefficient, this would be equal to 1 over the square root of 81 minus 1 over 1 over square root of 81 plus 1. Okay. So if we substitute these values, we get the following, we get minus 0.8. And by the way, this is smaller than this, so apparently we get a reflection coefficient which is a negative value. This is what we get. Meanwhile, for the transmission coefficient, this tau, we had the expression which was equal to 2 eta 2, so this is what we wrote, over eta 2 plus eta 1. And this whole term, we can also write this one, this can be equal to 2 times the square root of E1R, E1 relative, over E1R plus E2R. So this is E1R, this is E2R, so you know medium 1 and medium 2. And as a result, we observe that the transmission coefficient is, 0.2. If we substitute all the values, we get here 0.2. And we get from here, we also observe that 1 plus the reflection coefficient is always to the transmission coefficient. So we confirm a relation which looks like this. Okay, so this is always true when we have plane waves which are incident on a specific interface between two completely different mediums, or mediums that are relatively have some similarities. Okay. Yeah. Now here on the board we have also some other material which we can discuss, which is the following. Now we said, so let's have a look for a moment. So this was medium 1, and this was the average energy flow in medium 1, and apparently it is flowing in this direction. So we have some energy which is net flow energy in this direction, and this is for medium 2, and this is also some net. Now in this interface, so this is our interface, okay. This one, let's assume that we have no losses, no energy is lost at that point. And this one is not even creating any new energy. Forget about this one, but the more essential one is the following. This is a medium which is not absorbing energy. Then what can we say? We can say that this quantity here should be equal to this other quantity here. Okay? If you have any objection, you can ask or you can put forward the possible options why this should not be true. But this is true simply for the sake of the principles of the energy conservation and assuming that we have a perfect interface, losses are zero. So if these two terms are equal to each other, then we can also conclude another relationship between the different parameters. And here we have to fix one thing. This is eta 1, okay? Because this was medium 1, we forgot to write it over Z, and this is eta 2. So one essential relationship is this, which relates how the reflection coefficient and the transmission coefficients are related. Let's keep this here. And now these number calculations allow me to take this away, or yeah. So we have the numbers minus 0.8 and 0.2. And for a moment, what happens if you equal this expression with this expression? So we see that this the EI0 squared, we observe it here and here, so we can cancel them away, right? We can also cancel the 2, this factor 2, we can cancel them. So we can say here actually the power average in medium 1 should be equal to the time average power density in medium 2. So this should be true, which means that this is equal to this. Then we have the following. Let's write this one first. We have 1 over eta 1 times 1 minus the reflection coefficient squared. This should be equal to 1 over eta 2 times what? Tau squared. Okay, so this is how these values are related to the relative change between the intrinsic impedance of medium 1 and the intrinsic impedance of medium 2. Okay. Now let's see something here. Well, so in this case, we observed that the reflection coefficient was what? Just for, so we derived this other relationship. Okay, we have this, but now let's have a look at this previous example. So the reflection coefficient, it was minus 0.8, which means that we have a lot of reflection, a lot of wave is reflected backwards. So, back. Incidence.
Professor?
Yes. No, I think we are almost there. I just wanted to formulate, let's ask, no, we're almost done, but can you answer this, Vesmir? So what is the percentage of the energy that is lost following this reflection?
Is there ideally none?
Say it again.
Is there ideally no energy loss?
No. Well, ideal case for any electronics engineer or someone who is working in wave propagation, we would like to have, for many applications, we would like to have zero reflected wave energy. Okay, so we want zero reflection. And the reflection wave in this case, this can be represented something like this. So the reflected energy term, this can be expressed as this power average incident, okay, divided by time average power density for the incident wave, okay. So How do we find this? We just consider the incident wave. How much is the reflected one? This is the incident wave times the reflection coefficient. So these two cancel each other. So in this example, for this specific material, we observe a reflection, an energy approximately 0.8 times 0.8. So it looks like an incident plane wave on actually these values for the relative permittivity, they belong to water. So water is a very good reflector. So we can, with the values that we just calculated, we obtained, let's say, that 64% of the energy, it is reflected back. Imagine for a moment that you want to make, let's say, an optical system, or you want to make a lens. Can you lend it? The lens, this has, okay, so this is a piece of glass, okay, and you want to have all the light to pass through your optical system. You don't want to lose power, and the loss of the power, it is because if you have an optical system, you want to send the data from this side to the other side, right? So you don't want part of the information to come backwards. And imagine an optical system which has like 3 or 4 layers, or let's say 5 layers. And then if we lose like 5% in each layer times 5 layers, you lose 25%. This is too much. And actually, this also it progresses progressively because you are very good in math, and you can correct me regarding this. You're going to say, Professor, you don't lose 25% because you lose in the second layer, you lose 5% of the 95% initial power, right? So we have 100 units, 5% loss is lost, you get 95 left. Then in the second layer, you lose 5% of the 95, and also all of these calculations you can do them. But in principle, you're going to lose something between 20 to 25% of the signal. You don't want to do that. What do we do in this case? In this case, we try to use principles of which we can assume that, imagine for a moment this region. So we have medium 1, and then we can go to medium 2, okay, which has some thickness, okay. This has some thickness D, and this thickness D, we can adjust it somehow so that we have 0 reflection, which means that if we have here E transmitted, we can adjust the index of refraction and the relative permittivity of this material, also with the thickness D, such that we have maximum transmission from medium 1 to medium 3. So in this case, we have medium 1, this is medium 2, and this is medium 3. And this is a field of study which is very essential, because being able to produce optical systems with 0 reflection, nowadays it's possible for us to do it. We can easily manufacture layers with the thickness in the order of the wavelength of the light, okay? So since we have this technical ability, and since we know also the mathematical apparatus how to do it, we can simply do that. But as a reminder, I just wanted to have a look of how we can, wait a second, how we can determine the energy loss as the wave is passing through different mediums. Now, this is all I wanted to say. Do you have any question? Okay, if you have no questions, we can still receive your questions later.